this is lecture 20, and in the next 4 or 5 lectures, we will look at this idea of irreducible decompositions, primary decompositions, and associated primes. So this is going to be more abstract than what we have done so far, but after we discuss the basics behind these things, we will come back to the computational aspects. But it will have to wait till we understand this, the reasoning, the thinking behind these topics. So recall that in the last lecture, we saw the following, that irreducible idea, that spec R, so this is recall, spec R is, okay, so P in min R. So what are these things? Vp means, so for an R ideal I, by Vp, so this is a new notation, and we will discuss today why we shouldn't be worried too much. Sorry, Vi is all the primes that contain I, okay? And this disagrees with our earlier notation of points at which elements of F vanish, but we will see today that these are not very different. Okay? So, and algebraically, this is the object that we would want to continue using. Okay? And then we saw that, so this is Vi, and min R is the set of primes that are minimal. So this is the set of minimal elements of spec R. So this is okay. So we would want to understand these things, and so in particular, we know that if we take spec of R mod I, this is the union of V of P, where P contains I and is minimal with respect to that property. Okay. So this is what it says, and this is independent of whether you take I or the radical of I. So same. So we get the same thing. We get the same right-hand side if we take radical of I instead of I. Okay. So this is an important, this is an observation. So there must be a relation between okay. So there must be a relation between the radical of I and the primes containing I, and this is so the relation is the following proposition. Radical of I is the intersection of primes containing I, P in spec R. So we already observed that radical of I would be inside, so let's go over that part. So I should say that one could have proved this result little earlier also, but I felt that the proof is really easy to state once we understand localization, and which is the reason why I postponed it till this stage. One did not need to know localization to prove the statement. Okay, so notice that notice the following things. Primes are radical ideals. Prime ideals are radical. Okay, and intersection of prime ideals is radical. Therefore, the right-hand side is radical ideal, is a radical ideal. Okay, so I is in the right-hand side, okay, which means that the radical of I is in the right-hand side. So this is the right hand side is the intersection. Okay, so this is the one containment. So again, this we already proved. I'm just recalling the statement, this side of the argument, but it is the other one that is very easy to state once we understand what localization is. Okay, so to prove the other direction, let's just, so we need to, so we know that, so we have established this. Okay, so let's just kill the radical of I in R, and then we want to prove that the right hand side is 0. Okay, or let's kill I. Okay, so replace I by replace R by R mod I. Okay, so then we want to show that the right hand side now replaced, so right hand side is inside the nil radical. Okay, so I replace the right hand side by the appropriate object. Primes containing I are precisely the primes of R mod I, and the left hand side becomes a radical of 0, the nil radical. So this is the nil radical. Okay, so let's take, so let A be inside P for all P prime with P containing I. Okay. Now let's consider the ring R localized at A. So this is, remember, this is the set 1, A square, that set inverted. Okay. So this is a multiplicatively closed set, and that we are inverting, and then this is the, that is. Now we know what the primes of a localization are. Spec of R localized at A is P extended to R localized at A, where P is in spec R and P does not contain A. Okay, what it says is P does not intersect this set, but if P intersects this set, it would contain some power of A, and hence it will also contain A. So it shouldn't do that. Okay, so that's the P does not contain A. Okay. So this is the condition for this. But what are the prime ideals that satisfy this condition? Because A is, remember, A is in every prime. I'm sorry, there is no I here. P in spec R. Yeah, sorry. I made a mistake. I've already reduced it to the case where I is 0. So P contains 0. So okay, let A be in the set. Okay, so which now implies that this is the empty set. Okay. Now, what sort of rings, what sort of ring would have a property that spec is empty? The only ring with that property is a ring in which 1 is equal to 0. Okay. So now this implies that 1 equals 0 in Ra. We had not ruled out such rings. We had never said that 1 is the multiplicative identity, 0 is the additive identity, and we had never ruled out that we never ruled out the case that these could be the same. In fact, the ring is 0 if and only if this is, so maybe let's add that as a remark here. This is if and only if Ra is 0. Okay. So the only ring with an empty spec is the 0 ring, in which the multiplicative and additive identities are the same. Okay. One could, any ring in which 1 is different from 0, then it will have a maximal ideal, and maximal ideal is prime, so spec is non-empty. Okay. Yeah, so now let's, I mean that statement is proved using Zorn's lemma. Okay. So therefore 1 is equal, so but when can 1 be equal to 0 in R over A? So this means that, so let's go back to this statement. So this is an aside just to think about what this means. Okay. So 1 over 1 is equal to 0 over 1 in U inverse R. Okay. So this is the so in the equivalence relation 1 comma 1 is same as 0 comma 1 if and only if this is by definition. I mean this follows it directly from equivalent to the definition. There exists some u in u such that u times 1 u times 1 minus 1 times 1 minus 1 times 0 equals 0. Okay, so this is 1 times 1 minus 1 times 0 equals 0, and this is the same thing as saying there exists a u such that u times 1 is 0. So in other words, 0 is inside u. Okay, so if you invert a multiplicatively closed set, the ring becomes 0 if and only if 0 is in the multiplicatively closed set. So now let's go back here. So this now means that hence in our question there exists some m such that a to the m is 0. So the multiplicatively closed set is elements of this form, and 0 is there means this is the property, and this is exactly A is nilpotent. Okay, so this is the proof of the this proposition. Yeah, so one could have written this proof without really using localization, but it's much easier to visualize the proof once one understands not even full generalities of the localization, just such multiplicatively closed sets and this observation. Okay, so now so that was just an aside which we could have done, which I wanted to do. I mean, this whole statement it's not immediately related to irreducible decomposition, but I just want this to be people to know this observation. Okay. Yeah. So now we want to discuss what is the relation between. So now we are back to the problem in the geometric version of the problem, which is that K is algebraically closed. Okay. R is the polynomial ring in n variables, and I is an ideal, and S is R mod I. Okay. Now we defined two things called spec of S, okay. And then we also defined a subset called the maximal spec of S. So this is the set of all primes, this is a set of maximal ideals, and we know what in this particular case what this one looks like. It is just the set of okay, so I want to change the notation from last time a little bit, from earlier lectures a little bit. Okay, so this is change of notation. Okay, so please keep this in mind in these immediate future lectures. So for an R ideal J, okay, by V of J we mean the subset of spec S such that P contains J. Okay. And by Zj we mean the set of elements A inside Kn such that f of A is 0 for all A in J. Okay. So this is what we had called V of J earlier when we were discussing Nullstellensatz, okay. But I want to call it Zj, and well, one justification why it's like zeros of J, so we'll just call it Z. Okay. So this is what we, so I want to keep these two sets different. And we will see. So I want to keep these two sets different at this stage, and we will keep them different. But we will see at the end of this discussion that it's sort of immaterial. I mean, there are different sets, but the irreducibility of one is same as the irreducibility of the other, etc., which is what I want to head to now. Okay. So just again, this is the set of primes containing J, all of them, and this is the set of points at which every element of F, F of J vanishes. Oh, sorry, this is for every F in J vanishes. Okay, and therefore we know what max spec. So let me just repeat this line here. So this is, we know that spec of S, this is just, we can think of it as just V of I. Okay, S is R mod I. Okay, so S is R mod I. So you can think of this as V of I inside spec S. And this one contains max spec S, okay, the maximal spectrum of S. And what Nullstellensatz told us, the description of maximal ideals of V of I, the description of points in V of I, this is of Z of I, that this is in one-to-one correspondence with Z of I. Okay. And what is the correspondence? A point A here goes to the ideal generated by x1 minus a1 and so on, xn minus an. Okay. So that's in one direction, that an n tuple, this A is an n tuple, it's in Kn, gives that maximal ideal, and every maximal ideal looks like that. That was Hilbert's one of the versions of Nullstellensatz. So I'll just write Nullstellensatz. Okay, that Z of I inside Kn is precisely in bijective correspondence with max spec. The max spec. We had given Zariski topology to this. We can induce a Zariski topology on the subset, and we can identify, give a Zariski topology on Z of I using this. Okay, so give Zariski topology here. Okay, then induce, this is subspace topology. Okay, and using that extended to here. Extend the topology here. Okay, so I hope what we are doing is clear. We have given Zariski topology to spec S by saying V of J, where J is an ideal of I, those are the closed sets, and this is a subset. So then we can induce topology on that, the subspace topology, and then this is, as sets they are the same, so just use this bijection to induce a topology on this set. Okay. And we can talk about irreducible subsets here and irreducible subset there, and so that's what we want to explore now. Okay. So now, okay, so we want to observe one point here which is relevant to this question. Okay, so observation. For every prime, let P be a, let P be a prime in R, where R is a polynomial ring in n variables and K is algebraically closed. Okay. Then P is the intersection of the maximal ideals M is a maximal ideal and M contains P. Okay. This is a so this is a property about polynomial rings over fields. One can remove this hypothesis. So the way we will prove this, remove this hypothesis. But the way we will prove this is we will write this as a corollary of Nullstellensatz. But one can remove this and still it is true, but proof of that is far more involved, and in fact that statement is so general that Nullstellensatz can be derived from it. So this is somehow this statement is closely related to the Nullstellensatz. As it is written with this hypothesis, this can be derived from Nullstellensatz. If you remove this, it is still true, but that is stronger than Nullstellensatz, and one can prove Nullstellensatz from there. Although that is not the approach that we are going to use. Okay, so, but anyway, let's just prove this special case. Okay, so this is what we want to show. So P is clearly inside the maximal ideal, the intersection of the maximal ideals containing P. So this is, this is the proof of the earlier of that observation. Okay. P is clearly inside that. Note, so now let's take an element inside here. So let F be inside the right hand side. So this is the proof of this inclusion, containment. Okay. What does that say? That says that F of A, so what are maximal ideals of this? They are of the form x minus A1, x and so on. So one can, so then F of A is 0 so what maybe sorry, before I say that, let me just explain. Okay, so let M be a maximal ideal containing P. Okay. This implies that, so write M as x1 minus a1 through xn minus an. Okay. This implies that the point a1 through an is inside V of P. Okay. Because if you take P is inside M, and if you reduce all of elements of M, and if you evaluate an element of P, it would go to 0, because every element of M itself will go to 0 when you evaluate at this point. Okay. So this is what it means. So now, so what does this say? If you take an F, which is on the right hand side, then we have taken every maximal ideal containing M, so which means we have taken every point inside V of P. So F vanishes at every point inside V of P. Okay. Therefore, F of A is 0 for all A inside V of P. Okay. Yeah, maybe, sorry, we should, I should have been consistent with my own notation. I apologize. This is what we had begun calling Z, not V. Sorry, Z of P. Okay. So now let's, what does this mean? So now Nullstellensatz says, one of the versions of Nullstellensatz we proved, says that F is in the radical of P, but P is a prime ideal, it is its own radical, which is what we wanted to prove. So this proves the other direction. So it is an important property of polynomial rings. I mean, we have seen it only for algebraically closed, that every prime is an intersection of the maximal ideals containing that prime. Okay, so now let's continue with our discussion about irreducible decompositions of specs S. Okay, so now, so again we have now S. R is a polynomial ring. okay, algebraically closed. Okay. S is R mod I. I is some ideal, and we wanted, so we have spec S and we have max spec, we have Z of I, okay, which is identified with max spec and is now a subspace of this. Okay. Now let's take an irreducible subset of this. Okay. So we know that an irreducible subset of spec of S is V of P. Let P be a minimal prime of S, then V of P is an irreducible subset of spec S. Okay. This we proved in the last lecture. So now we ask, what about V of P intersect Z of I? This is just, remember, this is just max spec. Okay. So we have a larger topological space, spec S. Inside that there is a smaller topological space, I mean fewer sets possible, fewer elements possibly. And if we intersect V of P with the smaller set, is it irreducible? So that's what we would like to understand. Okay. So suppose, okay, suppose V of P intersect Z of I is some Z of J1 union Z of J2. Okay. So this, suppose this is the case, but see, we can simplify this a little bit. V of P is some subset of this. It intersects Z of I, which is the maximum spectrum of S of A, is, we can just take Z of P itself, or technically P is in spec S. Let Q be its contraction in R. That's also a prime ideal. And notice that V of P intersect Z of I. So here Q is an ideal of S, so Q contains I. I mean, P is an ideal of S, so Q contains I. So this is the same thing as V of P intersect Z of Q itself. Any maximal ideal containing I, and here, because of this condition, containing P will just contain Q. I mean, it's okay. So this will be the statement. Okay. So I mean, sorry, why did we reduce it like this? So replacing S by S mod P, okay, we can assume that S is a domain. Okay, and then the question is, so S, remember, S is still a quotient of R. It's still a quotient, not arbitrary S. Okay, so now we have a polynomial ring in n variables over an algebraically closed field, this R, and a quotient ring which is a domain, and then, so it is reducible, spec S is reducible. Okay, and we want to ask, so we ask, is max spec irreducible? Okay. If not, then otherwise, if not, so the answer is yes. If not, there exist ideals J1 and J2 in R such that Z of J1 union Z of J2 is, probably we do not need by contradiction, but nonetheless let's go ahead, is equal to max spec of S, which is same thing as Z of Q. Okay. So what does this say? Okay. So so then notice that Z of J1 union Z of J2 is Z of J1 J2. This was one of the it is also the Z of the intersection, and it's also Z of the product. This is one that we had proved. We have been using the word V at that point, but now I want to think of them as 0 sets and call them Z. As we said, we will discuss. So this implies that J1 J2 is in the radical of Q, which is Q itself. This is again by Nordström's answer. Okay. The only way this is going to be the whole space is that this ideal is nilpotent, or in other words, thinking of it in terms of R, it's radical of Q, and which is 0. Okay. But so this would imply that J1 is inside Q, or maybe one should just try to prove that. Okay. So let if J1 is inside Q, then there is nothing to prove. Okay. So maybe let's write it out properly. Okay. So we claim that J1 is inside Q or J2 is inside Q. Okay. Assume the claim for now, and we'll prove the claim in a minute. This implies that Z of J1 is equal to max spec S. Okay. But then this is a contradiction, since we assume that this was an irreducible decomposite. I mean, these were. So when you say if not, there exist ideas such that this is true, then although I didn't say it explicitly, we implicitly assume that neither of them is equal to this. Otherwise, there is nothing to prove. The problem is, I mean, if not, the assumption if not implicitly assumes that these are distinct from Z of Q, although I didn't write it here. So. Okay, so neither of them is equal to Q, but here we are concluding that one of them is equal to Z of Q. So therefore, this is a contradiction. Okay. Now to prove the claim, so this is just a general fact. If a product of ideals is inside a prime ideal, then one of the ideals is in it. Okay. Without loss of generality, we may assume that J1 is not inside Q, because if J1 is inside Q, then there is nothing to prove. Okay. So let A be inside J1 but not in Q. Then for all B inside J2, AB is inside Q, so B is inside Q, which implies that J2 is inside Q. Okay. So this is just a general fact about a product of ideals inside a prime ideal. Okay, so let's just go back and review what we just discussed now. So this is the end of the discussion, and this is the end of the lecture for this lecture. Okay, so let me just go back and just quickly review what we did. Yeah. So we have an algebraically closed field, and S is R mod I. R is a polynomial ring. And we have two sets that we have discussed so far with topology, Zariski topology on this, and the induced Zariski topology on this when this is identified with the maximum spectrum of S. And we ask, if you have an irreducible subset of spec S, does its intersection with the maximum spec give an irreducible subset of the maximum spec? So that's what we are asking here. Okay. VP intersect Z of I is it irreducible in, so the assumption here was that it is irreducible. Okay. Is it irreducible here? That's what we want to know. Okay. So let's assume that no, that there is some like this, but the point is P contains I, so let's Q be the inverse image, and VP intersect Z of I, which means all the maximal ideals containing P, maximal ideals of S containing P, but that is just the same thing as, we can rewrite it like this, it is just maximal ideals containing Q. Okay. So then replacing S by S mod P, we can assume that S is a domain. Okay. So that spec of S itself is irreducible. It just simplifies the notation to proceed further. And then we ask, under this assumption, if spec S is irreducible, is the max spec irreducible? Okay. The answer is yes. If not, so we are by going by contradiction, there exist ideals J1 and J2 in R such that their respective zero sets are proper subsets of max spec Z of Q, but the union equals Z of Q. So such a thing exists. So then this is the product. So then there is a claim, and we prove the claim. But the claim leads to a contradiction because Z of J is the maximum spec. Sorry, J1 is equal to Q or J2 is equal to Q. So Z of J, sorry, not J1, but some Ji, max spec for I equals 1 or 2. Okay. So it then remains to prove the claim, and the claim is quite straightforward. All that it uses is that there is one element inside J1 not in Q, therefore every element of J2 should be inside Q. Okay. So this is the end of this lecture.